won't get too,
Okay, sorry.
yeah, hopefully we won't get too much snow coming up.
Yeah.
Thanks. Good morning. The last group of materials I want to talk about in two lectures today and next Monday. And as a reminder, next Wednesday, we don't have a class because of Thanksgiving. But monolithic refractories is the last group here before we talk about how to design a refractory. But we'll go over the background of these materials, the raw materials, some of the phase diagrams, how they're processed and how they're used, and the microstructures and properties. So very simply, a monolithic refractory is a mixture, refractory mixture that's applied on site in the unfired state. It forms a continuous mass or structure. So it's installed in situ. There are no joints. It forms an integral structure. So the advantage, one of the advantages anyway, the absence of joints, that has a clear advantage. Joints are usually the weaker areas where corrosion takes place more rapidly than through, let's say, a solid brick. So if you eliminate the joints, you have an advantage in terms of corrosion resistance. These materials can be dense, very dense, surprisingly dense, especially in comparison to a pressed brick that can be even denser. And they can also be insulating with high porosity levels greater than 45%. So they're applied on site. The bond development occurs during use. So whatever the use temperature is, that's where the bonding takes place. So there's different types of bonds. There's a hydraulic bond. So this is hydraulic setting at room temperature. This would be a cement, like a calcium aluminate cement. It's a high temperature cement. Chemical bonding, um, that occurs by setting of an inorganic or a combination of organic inorganic reaction. Takes place at room temperatures, or it could take place at higher temperatures, but it will most likely take place at temperatures below where the ceramic bond takes place. And as far as the ceramic bond is concerned, that's what happens at high temperatures where the sintering takes place. And there are two mechanisms for forming a ceramic bond. One is solid state sintering and one is liquid phase sintering. I'll spend a few minutes going over these. So the advantage of a monolithic refractory, there's no shaping, so you don't have to press a brick or cast or slip cast a shape. There's no firing. The firing takes place in the actual application when the furnace is brought up to temperature. You can cast or fabricate complex shapes. The placement of a monolithic is relatively simple. It's economic. And if you have erosion, corrosion, and you need to do repairs, you can repair it with the same material so it bonds to itself. And I just mentioned there's no joint, so it's jointless. That gives greater corrosion resistance and greater wear resistance. So there's a whole range of monolithic refractory products. There's castable mixes, plastic mixes, ramming mixes, gunning mixes, shotcreting mixes, and mortars. So those are the most common. There's a few others that are less common. Dry vibratable mixes, injection mixes, and surface protection mixes. These are sprayed on. And tap hole mixes, primarily for blast furnaces. So for the castable mixes, they can be either dense or insulating. Uh, they may have a chemical bond. More commonly, they'll have a hydraulic bond. So if it's a cement, and this would be a high temperature calcium aluminate cement, there's 5 different possibilities here based on cement content. So RC is the standard refractory castable. It's the one that's been in existence the longest. They're the original compositions. They have a high cement content. And then as you go down this column, the cement content decreases. So there's a medium cement refractory castable, a low cement refractory castable, and then an ultra low cement castable, then finally a castable without any cement. The cement was eliminated because of the calcium in the cement. If you're using it in contact with aluminum and silica, it does form some low melting compounds. So the trend from high cement to no cement eliminates the reaction between calcium and aluminum and silica. So standard refractory castables can be cast, or rotting is a way of vibrating it, or vibration. The lower cement content castables usually require vibration. They may also be self-flowing if the particle size is adjusted so that they flow under their own weight. And then shotcreting is a form of gunning where the castable is applied wet. So these castable mixes are simply pre-mixed compositions of a refractory aggregate or grain, the matrix components, the bonding agent, and maybe some small amount of an admixture to adjust flow or rate of the reaction. So the hydraulic cement is a calcium aluminate cement. It's a high temperature cement. So the conventional castables were made with 15 to 20 weight percent cement. And then the medium cement castables, maybe 8 to 15 weight percent cement. Then the lower cement materials, 4 to 8 weight percent cement. And finally, the ultra low cement materials are usually less than 4 weight percent cement. And then you go all the way down to no cement. I mentioned that eliminates the CaO or the lime. When you have CaO, SiO2, and alumina, Al2O3 present, that can form some low melting phases. So the use temperature goes up as you go down in cement content. And if you don't have any cement, you're going to have a bonding agent. So that's usually a hydratable alumina or a colloidal silica. You can also have a chemical binder in these castable mixes. Phosphate is a possibility, alkali silicates, Al, H2PO4 taken 3 times as phosphoric acid, and then your alkali silicate. This is a sodium silicate, Na2SiO3. These are usually 2-component systems with a dry component that's mixed into the castable, and then there's a liquid activator. So besides castables, there's plastic mixes and ramming mixes. These are shapeable mixes. Again, plastic and ramming mixes. So in these materials, you use some type of pneumatic hammer to place the material. There may be a clay binder or a phosphate binder. So the plastic mixes are supplied in a plastic form. They're pre-compacted blocks, usually on the order of a cubic foot. So these are plastic and ready to be installed. And then the lining is built up by using a pneumatic hammer to place them. The ramming mixes are loose powders, so they're supplied usually moist in the friable state. So then those powders are compacted with a pneumatic hammer. There's also gunning mixes and shotcreting mixes. These can be dense or insulating. They can have a chemical bond, a hydraulic bond, and at high temperatures, they're going to form the ceramic bond from the sintering, whether it's solid state or liquid phase sintering. So either one of these, whether it's a gunning mix or a shotcreting mix, you're using an air pressure to spray this material through a nozzle. Gunning mixes can be installed cold at room temperature, or they can be installed hot at an operating temperature for a repair, hot repair. Shotcreting mixes would be installed cold at room temperature. So they can have a hydraulic cement binder or a chemical binder. So the gunning mix is supplied dry. It's run under pressure through a nozzle. The water addition takes place at the nozzle. So the dry mix is going through the system under air pressure. Water is added at the nozzle, and then that material is gone into a furnace lining, such as a wall, or floor, or ceiling. The shotcrete mixes are pre-mixed with water to the proper consistency, and then that slurry is shot under pressure through a nozzle. And that, again, builds up a wall or a roof or a floor, the lining of a furnace. And there's usually an accelerator that enhances the solidification rate. And then we also have mortars. Mortars are just fine powders. They can be heat setting or air setting. So a mortar is just a very fine powder plus a binder of some type. It can be heat setting, so that's hardens due to some type of chemical reaction or this ceramic bond that forms at the higher temperatures. It can also be air setting. That's usually due to some type of chemical reaction or hydraulic cement formation, and that forms at room temperature. And then the last group of monolithic refractories used in much smaller quantities. The dry mixes are dry vibratables. There's injection mixes, surface protection mixes, which are sprayed on, and then tap hole mixes, which usually contain a pitch or a tar. So these dry vibratables, the particle size is adjusted so that when they're vibrated, they compact to a very dense material. They're thermosetting. So there's a sintering aid or binder that forms helps form the ceramic bond at high temperatures. The injection mixes are just a mix that's injected into a void or a gap at high pressure, and those are just fine powders. If you have a surface protection material, again, it's applied by a spraying technique. And again, it's a fine powder plus some type of bonding agent. And the tap hole mixes, there are mixtures of clay plus an organic binder, usually a pitch, and that provides residual carbon. And it seals tap holes, such as tap hole in a blast furnace or any other operation where you have a tap hole for pouring steel or slag. So this pie chart shows the use of the different types of monolithics. About 46% are cement bonded with the calcium aluminate cement. About 26% are phosphate bonded. 16% may be bonded with a resin like a phenolic resin. A colloidal silica or a colloidal alumina, maybe 6%. A silicate bond, maybe 4%, and then the hydratable alumina bond, maybe 2%. So almost half of these materials are still bonded with the cement. So the different kind of raw materials, we've gone over just about all the different kinds of raw materials available, but this is a typical particle size distribution. The coarser aggregates start out maybe 1,000 microns, 1 millimeter, and go up to maybe 20 millimeters. And then there's intermediate aggregates, so going down in size, maybe 100 to 1,000 microns. Then the larger fines are maybe 10 to 100 microns. The smaller fines are maybe 1 to 10 microns. And then you have micron size fines around 1 micron, and then the super fines are less than a micron. So the coarser aggregates are usually polycrystalline. They actually are flow inhibitors. So they inhibit the flow of a castable or a gunny mix. The fines are usually single crystals or even amorphous materials. These enhance the flow, and they're the reactive components that provide the bonding. So this is what typical sizes might look like in these materials. And usually the refractory aggregate is about 40 to 80 weight% of the monolithic. Batch modifiers, this is for the matrix, maybe 5 to 30 weight%. Bonding agents like the calcium aluminate cement, maybe 2 to 50 weight%. And then additives to accelerate reactions or retard reactions or enhance flow. Additives also would include antioxidation agents. These are present in a small amount, less than 5 weight%. So for the different types of aggregates, these are alumina and aluminosilicate aggregates. So we have the alumina content, the silica content, and then the service temperature in degrees C. So the highest alumina content would be a tabular alumina or a white fused alumina, to be about 99% alumina. And they have a pretty high service temperature, maybe 1870 degrees C. And then we also talked about brown fused alumina, has higher iron oxide content. Maybe it's 94 to 98% alumina. Some silica is present, and then the use temperature starts to drop a little bit, 1760. Can also have bauxite and mullite. So bauxite maybe close to 90% alumina, and mullite a little bit higher than 72% alumina. And then as we go down, the silica content is increasing. Maybe there's a kaolinite clay that has bauxite present, so a bauxitic kaolin. So the alumina content is going down, and andesite. And then our different types of clays, a kaolinite or a flint clay, they're less than 50% alumina and a little higher than 50% silica. So now we're going down to maybe 1650 degrees C. Pyrophyllite has pretty low alumina content, lower than 30%, and the silica content is higher than 65%. So the use temperature goes down quite a bit, 1425. And then the fused silica has no alumina. It's basically 100% silica, and it crystallizes at a low temperature. So the use temperature, when it's still amorphous, is below 1370 degrees C. So those are some alumina silica aggregates used in these monolithics. We've also talked about periclase or magnesite, dolomite, the magnesium aluminate spinel, chromite, silicon carbide, and AZS alumina zirconia silica. So this is the chemical formula, and then this is the percent of each chemical. So an MgO aggregate, maybe 90 to 99% or 98% MgO. Dolomite might have up to 59% CaO and up to 40% MgO. And then the spinel doesn't have to be stoichiometric. It is quite a range. So maybe 26 to 32% MgO, then the balance being alumina. The chromite has some iron oxide, maybe up to 24%, Cr2O3 up to 46%, and then the alumina maybe up to 29%. Silicon carbide depending on the purity, 90 to 99%. And then AZS. So this is the alumina range, 42 to 45%, the zirconia range, 36 to 37, and SiO2 is the balance, 16 to 17%. So we have all these alumina silicate aggregates, different other type of aggregates. Those are all dense for forming dense castables or monolithics. We can also have insulating aggregates. Vermiculite, perlite, and hadeite all expand when heated. The vermiculite is a hydrous phyllosilicate. Perlite is a volcanic type glass, and hadeite is a shield that expands when heated. So these expand, create porosity, and have low density. So these are the densities in kilograms per cubic meter, and then the surface temperature. So the first three here, vermiculite, perlite, and hadeite, are pretty low temperature materials. Fly ash can be made in a bubble form, so it's a hollow sphere, depending on the chemistry, maybe 1200 to 1525 degrees C. You can crush insulating fire bricks, and depending on the chemistry of those bricks, that determines the use temperature. Clay grog is good to maybe 1650 degrees C. And then the highest one here in terms of use temperature is bubble alumina. So it's a hollow alumina sphere that is good up to 1800 degrees C. So these are porous aggregates for insulation. And then there's a variety of fillers and modifiers. So you could take any one of the aggregates we talked about, mill it very fine for the matrix. So any of these chemical formulas we just mentioned, and they're going to be in the matrix. So they're going to control the chemistry, the phases that develop the mineralogy. They're going to affect how the bond forms. And we have alumina here. It can be calcined or reactive. So a calcined alumina, again, is going to control the chemistry, what phases development, what phases develop, and then how the bond forms during the sintering process. If it's a very fine particle size alumina, very reactive, it's going to affect the flow and rheology, and it'll also affect the bond development in the matrix. For silica, quartz is usually inert at low temperature, so it's there to control the shrinkage. It's inert and stable. And there's also fume silica, which is a very fine silica that affects the flow or rheology, and also how the bond develops, how the phases develop in the matrix. Fume silica is usually added to react with a reactive alumina to form mullite in the matrix. And then MgO, again, affects the type of bond and phases that develop. If there's a reactive alumina present, MgO will react with that to form a spinel. And a spinel has good corrosion resistance, so reduced metal or slag attack. Other modifiers, kyanite, and that forms spinel, 3Al2O3. There should be 2SiO2, whatever book I took this out of. Put a 3 instead of a 2. Kyanite is there for shrinkage control. If you remember, it increases in size when it forms mullite. So it's there for shrinkage control, and also how the chemistry develops, how the phases develop in the matrix. Spinel is a filler. It reduces metal and slag attack. Silicon carbide is added because it improves the thermal conductivity, has low thermal expansion, so it also improves the thermal shock resistance. Clays or hydrated aluminosilicates, They're generally fillers, but they also can control the rheology. Zircon is there for primarily corrosion resistance, so it reduces slag and alkali attack and metal attack. Graphite or amorphous carbon, that does a lot of things. It reduces the metal or slag attack because it's non-wetting. It increases the thermal conductivity. It lowers the thermal expansion and improves thermal shock resistance. We talked about antioxidants, aluminum metal, silicon carbide, and boron carbide, plus other antioxidants. They protect the carbon if carbon is present, and they also react and modify the matrix. The reaction products tend to fill pores and make the material stronger. Polymer fibers and metal fibers. Polymer fibers are added to burn out and improve permeability. Allows water to be removed through the steam during dry out. Metal fibers are added to toughen the material. Actually, it really improved thermal shock resistance. Nano additives would be very expensive, but they would affect how the phases develop in the matrix. And fly ash is another possibility. If it's in bubble form, it's a low temperature filler for insulation. And then the other additives or admixtures, these can accelerate a chemical reaction. They can retard a chemical reaction. They can control the pH. They can reduce the water content of a monolithic. The lower the water content, the lower the porosity, the denser it'll be. And they may also affect the rheology, how the material flows. So lithium carbonate, calcium hydroxide, sodium carbonate, sodium bicarbonate, sodium citrate, sodium phosphates, sodium polyacrylate, polycarboxylate, citric acid, and boric acid. And you can see where the X's are. That's the property or function they control. So those are the general types of materials that are used to make up monolithics. So I like to go into some detail on some of these. Again, the calcium aluminate cement is the most common binder. So it's a hydraulic binder. There's also hydratable alumina. That's a hydraulic binder. So whether it's a calcium aluminate cement or hydratable alumina, they're going to form hydrates at room temperature. That provides the green strength for the monolithic material. But then they're all going to decompose. These hydration products will decompose. So generally around 200 to 400 degrees C range, the hydration products, whether it's a cement or hydratable alumina, they're going to decompose. As soon as they decompose, you're going to lose your green strength. So there's a strength loss, there's a porosity increase. Then eventually, as you go up in temperature, you're going to form ceramic bonds, whether it's solid state or liquid phase sintering. And these occur at higher temperatures. And as soon as the sintering takes place, the strength is going to increase again. There are mineral and chemical binders. So phosphoric acid, sodium silicate are some chemical binders. These give green strength at temperatures up to 150 degrees C or even a little bit higher. And then eventually, as you again increase the temperature, you're going to form a ceramic bond due to a sintering mechanism. And the ceramic bonds again will increase the strength at high temperatures. The slow gel or colloidal suspensions of silica. So this material forms a gel. It provides the green strength at room temperature. And again, that gel will decompose. It'll get weaker. And then finally, at the higher temperatures, the ceramic bond, due to, again, a sintering mechanism, will increase the strength. And then I've been mentioning ceramic bonds due to solid state or liquid phase sintering. In any of these two mechanisms, the process of forming a rigid and usually dense body from an aggregate of powder particles. So you're providing strength by forming a rigid body. Sintering usually takes place at temperatures higher than 600 degrees C, typically much higher than that. There's an increase in density, there's a decrease in pore volume, there's an associated shrinkage, and there can also be crystal growth. So the crystal size may increase. So I'll spend a few minutes going over each one of these: solid state sintering and liquid phase sintering. So during solid state sintering, you remove pores between the particles. There's shrinkage because you're removing the porosity, and then you're forming bonds where these particles are in contact. So the driving force for densification is simply the reduction of surface energy by elimination of surface area or these solid vapor interfaces. So the whole driving force is reduction of surface energy. Surfaces have higher energy than the bulk, so you want to eliminate surface area to reduce the energy. So there's various mechanisms of material transport. There's an evaporation condensation mechanism, and there's various solid state mechanisms. There's surface diffusion, grain boundary diffusion, and lattice or bulk diffusion. So there has to be material transport to create these bonds between the particles. So A here is just a loose powder compact. So you have these particles. There's no temperature applied yet. So they're perhaps touching in contact. And then in the initial stage of solid state sintering, material is transported to the neck regions. These are regions of high curvature, higher energy. So they start forming bonds. You start forming bonds at these neck regions. So the material becomes stronger, it becomes rigid. And as you go up in temperature or hold for longer times, there's an intermediate stage. These contact regions continue to grow. So the neck regions expand. The pores are decreasing in size. And then finally, when you have a sintered product, you can see the distinct crystals and the grain boundaries, and basically most of the porosity should be eliminated. So that's what happens during solid state sintering. So there are various mass transport mechanisms. Material has to move to these neck regions. So there's 6 different ones outlined here. One is the surface diffusion. So material is simply diffusing along the surface of these particles. There are actually 3 particles here, and they have grain boundaries. Material moves along the surface and deposits in the neck region. That builds up the neck region. There's volume diffusion. So material moves from the volume of this material to the neck region. There's evaporation condensation. So material evaporates off of the surface and deposits in the neck region. It has a lower partial pressure here. There's a volume diffusion. So material moves from the grain boundary through the volume to the neck region. There's another volume diffusion where material moves from dislocations, crystal defects, to the neck region. And then there's grain boundary diffusion. Material is moving along the grain boundary. All of these mechanisms are depositing material in the neck regions and building up the grain boundaries. So some important features of solid state sintering. The shrinkage increases with time at a constant temperature. The shrinkage rate decreases with time at a constant temperature. and the shrinkage rate is inversely proportional to particle size. So the finer the particle size, the more reactive, the faster the shrinkage rate. And the shrinkage rate is going to increase with temperature. So if you increase the sintering temperature, the shrinkage is going to take place even faster. In liquid phase sintering, you form a liquid and material is transported by viscous flow. So this liquid should wet the solid, should spread over the solid, and the particles will be drawn together by capillary pressure. So the driving force is simply pressure differences due to differences in local curvatures. So that's going to move material into the high curvature areas, which are these neck regions. So the mechanism of transport here is simply by viscous flow. So again, in liquid phase sintering, you form a viscous liquid, it flows, wets the solid, and then draws the particles together by capillary pressure. So one here has a large volume of continuous glassy phase. So the white areas are the aggregates or crystals. The black area is a large volume of glass. B is a much smaller volume of glass. So the black area would be the areas containing the viscous liquid, and the white areas are the individual aggregate or crystals. And then C is a condition where the glass that may be present, like in B here, it's amorphous, it crystallizes. So you're usually trying to crystallize a glass into a higher temperature material. So some important features of liquid phase sintering. So again, it's usually going to be a silicate glass that forms a viscous fluid. The sintering rate is inversely proportional to particle size. So again, the finer the particle size, the higher the densification rate. The lower the viscosity of the liquid, the higher the shrinkage rates. The shrinkage rates again increasing with temperature because the viscosity of the liquid is going to decrease. And you can control or try to control the viscosity of the liquid by controlling its composition. So the more fluxes you have present, maybe the more alkali, the lower the viscosity. So I'll go over some of these in more detail. The calcium aluminate cement is the first one we'll look at. It's the most widely used of the hydraulic binders. It has pretty fast settings, 6 to 24 hours it sets, and it has a high cured strength. So there's three types of calcium aluminate cements, and they're all based on purity. So there's a low purity, an intermediate purity, and a high purity. So the two main components are Al2O3 and CaO. So the low purity material is maybe 39 to 50% alumina, going to higher purity, 55 to 66% alumina, and then the high purity is maybe 70 to 90% alumina. And then the lime content goes down as you go up in alumina content. So the low purity may be 35, 42% lime, higher purity 26%, and then the highest purity maybe 9 to 28. So as you go up in purity, you eliminate Fe2O3, and you also eliminate SiO2. And going up in purity level, you're also going to go up in use temperature. So the low purity is going to be useful to maybe 1400 C, the intermediate purity 1400 to 1600 C, and high purity maybe 1800 degrees C. So that the calcium aluminate cement by itself, if it's high purity, is quite refractory. So the phases that develop in this cement, and this is in cement notation. So C is CaO, A is Al2O3, S is SiO2, S star is SO3, F is Fe2O3, and T is TiO2. So this is low purity, intermediate purity, and high purity. And this is the hydration rate. So this group of materials hydrates quickly, this group hydrates slowly, and then the final group here doesn't hydrate at all. So the primary phase in calcium aluminate cement is Ca. That's the primary phase that hydrates. Ca2 is another major phase that hydrates. Present in much smaller amounts is C12A7 that also hydrates. Lime can hydrate. And then if you have sulfur present in this low purity material, this compound C4A3S can also hydrate. Other materials that hydrate are C2S, C4AF, and C2AS. And when you go to the higher purity, you won't have any free lime or sulfur or any of these other slow hydrating materials. A calcium titanate or alumina, especially coarse alumina, they're not going to be hydrating. So Ca, Ca2, and C12A7 are the primary phases in these calcium aluminate cements that hydrate. So we'll just look at one of these materials. The primary phase is Ca, that's CaO, Al2O3, and we'll look at how this material sets as a function of temperature. So you really have three choices. You can cast those at room temperature. If it's a hot summer day, you're going to be higher than room temperature, and if you're casting in the winter, you're going to be lower than room temperature. So this is at room temperature. 2CaO Al2O3 plus XH2O forms this compound here. 2CaO Al2O3, then it's X minus 3H2O plus this hydrated alumina Al2O3 3H2O. X will be 11 at room temperature. So what you end up with is 2CaO Al2O3 8H2O, and in cement notation, that's simply C2AH8. So this is the hydration product at room temperature for Ca. You also have this hydrated alumina, which is AH3. So when you heat this up during the use application, the C2AH8 dehydrates around 170 to 195 degrees C. The AH3 dehydrates around 210 to 300 degrees C. So higher than 300 degrees C, this material becomes more porous and quite weak. So if you hydrate at a higher temperature greater than 35 degrees C, here's your Ca, which is CaO Al2O3, so 3Ca plus XH2O forms this compound, 3CaO Al2O3 X minus 6H2O, and then this is AH3 again. So in this case, X is going to be 12, so that's going to yield this compound, 3CaO Al2O3 6H2O, or in cement notation, C3AH6. So now this compound C3AH6 is going to dehydrate between 300 and 360 degrees C. And then the AH3, the hydrated alumina, is still going to dehydrate around 210 to 300 degrees C. And then the other possibility, if you're in the middle of winter somewhere and you have no heat in a plant, the temperature is going to be less than 21 degrees C. And this is the reaction. This is Ca again plus XH2O. And this is your reaction product, 2CaO Al2O3 X minus 3 H2O plus your hydrated aluminum gel again. So X is going to be 13. So now you're going to end up with CaO, Al2O3, 10H2O. So there's a substantial amount of water in this product, and that's CaH10 in cement notation. So CaH10 is going to decompose between 100 and 130 degrees C, and the hydrated alumina AH3 again is 210 to 300 degrees C. So the most desirable situation is to cast at the higher temperatures above room temperature. The least desirable is to cast at low temperatures below room temperature. So below room temperature, you're going to have CaH10. At room temperature, you're going to have C2AH8 and AH3, probably a gel. You're also going to have AH3 at the lower temperature too in a gel form. And then if you cast at above room temperature, you have C3AH6 plus AH3 again. It's probably going to start to crystallize. So this density of this product is 1.72 grams per cubic centimeter. That's CaH10. C2AH8 is a little denser, 1.95. And the AH3 gel is 2.42. And then finally, C3AH6 is even denser, 2.52. And again, AH3 is 2.42. So if you start out by casting below room temperature and you have CaH10, there's a 37% volume change when you go to C2AH8. And when you go to C3AH6 by increasing the temperature, there's a 53% volume change. So you don't want to start out with CaH10 because you have all this excess water and you have these large volume changes. So casting at room temperature removes this volume change. Casting at higher than room temperature removes this volume change. So avoiding those volume changes, you're going to end up with a much denser, stronger material. So again, casting a calcium aluminate cement, you should do it at room temperature or slightly higher. So these are the main cementitious compounds. Ca is the primary one, then Ca2 in lesser amounts, and finally small amounts of C12A7. These are the hydration products we just went over. AH3, CaH10, C2AH8, C3AH6. Again, this is the product above room temperature. This is at room temperature. This is below room temperature. And then when you take it up to high temperature and you sinter this material, you're going to end up with alumina, Ca, and Ca2 again. And these are the melting temperatures. So Ca is still pretty high, 1605. Ca2 is 1750. And alumina is about 2050. These are all in degrees C. So if you look at the phase diagram between CaO and Al2O3, so this is 100% Al2O3 on the right and 100% CaO on the left. And we're going from maybe 13 to 2300 degrees C. So here's Ca6, Ca2. There's another compound here, C3A5, that occurs at lower temperatures. Here's Ca, and here's C12A7. So going from right to left, you're increasing the lime content. And you can see what's happening to the use temperatures here. Here's Ca6. It's somewhat under 1900. Then Ca2 is getting closer to 1700. Ca is about 1600. And C12A7 is about 1400. So these eutectics and solidus curves are just decreasing as you increase the lime content. And I mentioned the trend to go to a low cement castable. So you can see why that trend occurs, because you can just see it on this phase diagram. Here's a ternary phase diagram between SiO2, Al2O3, and CaO. So SiO2, Al2O3 has one compound, mullite. So we went over this phase diagram quite a bit when we talked about aluminosilicates. So these all produce stable high temperature compounds such as alumina and mullite. But when you have lime present, you start getting into this region here in the middle of this phase diagram. You have an orthite forming, which is CaAl2O3, 2SiO2, and galenite, which is 2CaO, Al2O3, SiO2. This one melts at 1550 degrees, 1553 degrees C. This is 1593 degrees C. But you start looking around the phase fields here, you see peritectics and eutectics, 1300 or so, a little higher than 1100, a little higher than 1200, some more 1300s. So the presence of lime in conjunction with an aluminosilicate refractory produces these low melting regions. So that's why the trend was to go to a lower cement content to eliminate the CaO, to move into these higher temperature regions and eliminate anorthite and galenite. The other hydratable phase is hydratable alumina. So these are used in the no cement castables. That completely eliminates the lime, the CaO, and that eliminates the formation of these low melting phases, anorthite and galenite. So hydratable alumina is just very fine particles of a reactive transition alumina, which is usually a row alumina. So these materials hydrate at room temperature and develop strength. And if you have a hydratable alumina in the matrix, and if you want to form the mullite phase, you can just add some fumed silica. So that the fumed silica reacts with the reactive alumina. Both very fine particle size materials are quite reactive. They'll form mullite, and you won't have these low melting phases present. So the reaction of a reactive alumina with water, 2Al2O3 plus 4H2O forms your Al2O3, 3H2O gel or bayerite, and it also forms a boehmite gel, 2AlOOH. So these crystals, when they crystallize, basically provide the green strength to the castable. It fills in the pore, fills in pores that are present, and the crystals connect the aggregates through the matrix. I mentioned fumed silica additions. These are byproducts when you produce silicon metal. Very fine particle size, 0.01 to 0.5 microns. And you add fumed silica to these monolithics for two reasons. The fine particles enhance the flow and allows the material to densify during casting or gunning or however you're applying it. And then I just mentioned the silica reacts with alumina in the matrix and forms mullite. So mullite is usually a pretty desirable phase because it is a high temperature phase, and it has good thermal shock resistance and good corrosion resistance. So Al2O3 plus SiO2 forms mullite, which is 3Al2O3, 2SiO2. And then I think we'll just go over the phosphates and probably maybe stop there. But phosphoric acid, H3PO4, reacts with the metal oxides. and hydroxides, and it forms various salts. The salts are the bonding agents. So in this alumina system, we have Al2O3 or hydrated alumina, AlOH3. They'll react with this phosphoric acid and form what's known as a monoaluminum phosphate, or MAP. So alumina plus phosphoric acid or hydrated alumina plus phosphoric acid are all going to form this compound, Al H2PO4, and that's taken 3 times, and there's going to be a water byproduct. So this is MAP, the monoaluminum phosphate. So when this forms, it stiffens the matrix, you lose workability, and the material starts to harden and strengthen. So when you heat this material up above 300 degrees C, the monoaluminum phosphate, or MAP, will decompose. So this material, Al H2PO4, and this is 3 times, is going to form this monoaluminum phosphate. Al2 H2P2O7, and that's taken 3 times, and there's a water product coming off. But then this will decompose into this aluminum metaphosphate. So Al2H2P2O7, and taken 3 times, it's going to result in aluminum metaphosphate, which is AlPO3, and that PO3 is 3 times. And there's additional water coming off. So this aluminum metaphosphate forms and grows over a wide temperature range, and it increases the strength, and it just forms in the matrix and bonds the material together. But then that monoaluminum phosphate, as you heat it up, is going to then change. So between 800 and 1,000 degrees C, it's going to react with alumina to form an aluminum orthophosphate, which is AlPO4. That's similar to the cristobalite structure. So AlPO3 taken 3 times plus alumina forms this aluminum orthophosphate. And that's the high temperature material that develops. It turns out that this monoaluminum phosphate, or MAP, is slow to harden at room temperature. It's a slow reaction. So sometimes MgO is added to set this material. So the reaction between MgO and MAP is exothermic. It generates heat. It accelerates the reaction. One of the disadvantages of using MgO to set this material is it does form some low melting magnesium phosphates. And when you have low melting materials, you're going to decrease the hot strength of these phosphate bonded refractories. So you're adding MgO to react with MAP. So at room temperature, and this ratio, P2O5 to Al2O3 plus MgO, if that's near 1, this is going to be a reaction product. It's MgHPO4 with 3 H2Os. And then as you increase the temperature to about 1,000, you're going to form AlPO4 plus this material, this magnesium phosphate, Mg3PO4 taken twice. This is a low melting material. At room temperature, and if the ratio is higher, 1.5, so the ratio of P2O5 to this sum, Al2O3 plus MgO, you're going to end up with this material, MgHPO4 taken twice, and as you heat it up to a higher temperature, above 1,000, you're going to form AlPO4, which is desirable, plus this one, MgPO3 taken twice, which is another low melting magnesium phosphate. So if you look at the phase diagram here, this is MgO and this is P2O5. It's not the complete phase diagram. It's the segment in the middle of the phase diagram. But you can see here these magnesium phosphates that form MgP2O5, 2-MgO-P2O5, and 3-MgO-P2O5. And you look at the melting points, 1165 C, 1382 degrees C, 1357 degrees C, and the eutectics are even lower, 1282 degrees C or 1165 degrees C. So you can use MgO to accelerate the reaction, but these are some of the reaction products, and you can see they're lower temperature materials. I think I'll stop here today, and then next time we'll finish up the raw materials and look at how these materials are processed and look at their microstructures and some of their key properties. So I think this is a good stopping point. It's about halfway through this lecture. So again, thanks for attending today. We have a lecture on Monday, and again, there's no lecture on the Wednesday before Thanksgiving. So have a good weekend, and I'll see you Monday. Thanks.
Thank you.
Thanks.